Another interesting example of circular motion are banked turns, which we see all around us when we're driving, getting on and off of freeways, etc. We see banked turns all the time. Maybe you watch auto racing on TV, and the tracks have those banked turns that enable the cars to take the turn at a higher speed than they would be able to take the turn on a flat roadway. So let's examine this a little more closely. We've got our car going around the banked turn. That's as good as I can do with my drawing ability. You get the idea though. Let's draw a free body diagram for that car. There's going to be a normal force up from the road, normal to the road, and there's going to be a force of gravity toward the center of the earth. I'm going to redraw my car. So here I have a cross section of that road. I'm just cutting a cross section of the road. The car is sitting on an incline here. Actually, it's coming toward us out of the page. And our normal force points perpendicular to the incline in this direction. Gravity points toward the center of the earth. And just to keep this problem simple, let's make this a frictionless surface. There's actually a speed that the car can go around this banked turn and make the turn, no problem, even if the surface is frictionless. So that's the case we'll look at. And I'll leave it up to you to look at cases where there's friction. We want to pick an appropriate coordinate system and split these vectors into components. Go ahead and do that. Well, we always want to pick the direction of the acceleration. I know when we deal with inclined planes, you're used to always putting the coordinate system aligned with the inclined plane and perpendicular to the inclined plane. But that's not what we're going to do in this case, because we want to pick the direction of the acceleration for our coordinate system. And our acceleration is going to point toward the center of the circular path. The car is going in a circular path, and the center of the circular path is over here. And this is the radius of the circular path the car is taking. So I want to pick the direction of my acceleration and perpendicular to that as my two directions in my coordinate system. The force of gravity is already in that coordinate system. I will leave it as is. But the normal force needs to split into components. So you can see now there's a component in this direction, and there's a component in this direction. And if the angle of the incline is theta, then the normal force breaks up this way as n cosine theta in the vertical direction, n sine theta in the horizontal direction. And you can see now why the car is able to go through a circular turn with no friction, because the normal force is pushing it toward the center of the circle, allowing it to stay in a circular path. So we can say the sum of the forces equals ma, and we can divide this up into our two directions, and we get the radial direction is equal to ma centripetal, and I always pick toward the center of my circular path as my positive direction in the direction of the acceleration. And that gives me n sine theta is mv squared over r. And I know that the sum of the forces in the vertical direction here have to add to 0. The car is not moving in the vertical direction. It's always at the same vertical location. So that tells me n cosine theta equals mg, the force of gravity. So this is a simple case where we don't have friction on our inclined surface, on our banked road. Normally there would be friction there. So if you want to do this problem with friction, go ahead and do that. But keep in mind that the friction force is a little tricky here. As you increase your speed and go faster and faster and faster, if your car is going really fast, what does your car want to do as it goes around that bank turn? Your car wants to slide up the hill. So if your car wants to slide up the hill as you go faster and faster and faster around the turn, what direction would the friction force point? The static friction force between the tires and the road would point down the incline if your car is going really fast. But if you slow down and you go slower and slower and slower, eventually you're going so slow that your car actually wants to slide down the incline because of the force of gravity pulling it down the hill. It wants to slide down the incline. And if your car is going so slow that it wants to go down the incline, what's the friction force going to do? The friction force is going to push up the incline to prevent your car from sliding down. So think about that if you take on a bank turn with friction.